You may be aware that I'm a huge fan of the YouTube channel 3 Blue 1 Brown, run by Grant Sanderson. Grant makes excellent videos about math and mathy aspects of other topics, so I'm letting him take over my channel for today. Grant, take it away.
A week ago, I put out a tweet showing a peculiar place where an ellipse arises, but what I didn't mention is that this arbitrary-seeming construction is actually highly relevant to a once-lost lecture by Richard Feynman on why planets orbit in ellipses. The construction itself starts by drawing a circle, and then choosing some point within that circle that's not at its center, what I'll call an eccentric point, and then draw a whole bunch of lines from this eccentric point up to the circumference somewhere, and then for each one of those lines, rotate it 90 degrees about its midpoint, and when you do that for all of the lines, an ellipse emerges in the middle. Out of context, this is a mildly pleasing curiosity, but there's a much deeper form of satisfaction on its way once you understand the full story surrounding this. Front and center of that story is Richard Feynman, who's famous in a number of dimensions. To scientists, he's a giant of 20th century physics, winner of the Nobel Prize for his foundational insights in quantum electrodynamics, among many other things. To the public, he's a refreshing contradiction to the stereotypes about physicists, a safe-cracking, bongo-playing, mildly philanderous nonconformist whose heavily Brooklyn-accented voice you've probably heard either relaying some bit of no-nonsense pragmatic wisdom about the only sensible way to view the world, or else some wry joke told through a crooked smile. But to physics students, he was an exceptionally skillful teacher, both for his charisma and his uncanny ability to make complicated topics feel natural and approachable. Many of the lectures he gave to a Caltech freshman course are immortalized in the now famous Feynman Lectures, whose 3 volumes you can find for free online. But not all of the lectures he gave made it into this collection. One in particular, a guest lecture given on March 13, 1964, entitled The Motion of Planets Around the Sun, survived only as an unpublished partial transcript with a smattering of notes buried in the office of one of Feynman's colleagues, until it was eventually dug up by Caltech archivist Judith Goodstein. Despite the absence of some crucial blackboard drawings to follow what Feynman was actually saying, her husband, David, eventually reconstructed the argument of the lecture, which the two of them published in a book titled Feynman's Lost Lecture, conveying both the lecture itself and the surrounding story in a really beautiful way. Here, what I'd like to do is give a more animated and more simplified retelling of the argument that Feynman was presenting. The lecture itself is about why planets, and other astronomical objects, orbit the sun in ellipses. It ultimately has to do with the inverse square law, the fact that the gravitational force pulling an object towards the sun is inversely proportional to the square of the distance between that object and the sun. But why? How exactly does that law give rise to an ellipse of all shapes? Of course, the gravitational attractions between different planets and moons and comets and all of that means that no orbit is a perfect ellipse, but come on, to a very good approximation, this is the shape of an orbit. You could solve this analytically, setting up the appropriate differential equation and seeing the formula for an ellipse pop out. But Feynman's goal with this lecture was to do something special, and to not rely on any heavy mathematical machinery. In fact, let's listen to him articulate his own goal.
I am going to give what I will call an elementary demonstration. By elementary does not mean easy to understand. Elementary means that nothing, very little, is required to know ahead of time in order to understand it, except to have an infinite amount of intelligence. There may be a large number of steps that are very hard to follow, but each step does not require already knowing calculus, already knowing Fourier transforms, and so on.
Yeah, that's all. Just a little infinite intelligence. I think you're up to that, don't you? I've done what I can to simplify things down further from his original lecture, but that's not to say that a good deal of focus won't still be required. First things first, we need some definition of an ellipse, otherwise there's just no hope of proving that that's the shape of an orbit. Some of you might be familiar with the classic way of constructing an ellipse using 2 thumbtacks and a piece of string. Use the thumbtacks to fix the ends of a small string in place, and then pull that string taut with a pencil, and try to trace out a curve while keeping that string taut. It's similar to how you might use a single thumbtack to construct a circle, where the fixed length of the string guarantees that every point you trace out is a constant distance from the thumbtack. But in this case, with 2 thumbtacks, what property are you guaranteeing about each point that you trace out? Well, at every point, the sum of the distances from that point to each of the 2 thumbtacks will be the full length of the string, right? So the defining property of this curve is that when you draw lines from any point on the curve to these two special thumbtack locations, the sum of the lengths of those lines is a constant, namely the length of the string. Each of these points is called a focus of your ellipse, collectively called foci. And fun fact, the word focus comes from the Latin for fireplace, since one of the first places where ellipses were studied was for orbits around the sun, a sort of fireplace of the solar system, sitting at one of the foci for a planet's orbit. Making up a little bit of terminology for ourselves, let's call this constant sum of the distances from any point on the ellipse to the two foci the focal sum of that ellipse. We'll get to the orbital mechanics in just a moment, but first, I want you to turn back to that construction that I showed at the very beginning, which is going to come up again later in the story. Remember, we take all of these lines from an eccentric point of the circle to its circumference and rotate each of them 90 degrees about its center. But what on earth does this have to do with the constant focal sum property I just described? You could just take my word for it that this emergent shape is an ellipse, but I think you'll be much more satisfied in the end if we take a little time right now for a brief sidestep into geometry proof land. First off, there are really only two special points in this diagram. There's the eccentric point from which all the lines emerge, and the center of the circle. So a reasonable guess would be that each of these is a focus of the ellipse. Given the defining property of an ellipse, you know that you're going to want to look at the sum of the distances from these 2 points to, well, something. Also, if you're doing any geometry problem involving a circle, you'll very likely want to draw a radius of that circle at some point, and to use the fact that this radius has a constant length, no matter where you draw it. I mean, that's what defines a circle, so you're probably going to need to incorporate that fact somewhere. With those two thoughts in the back of your mind, let's limit our attention to just one of these lines, touching some point P on the circle. Remember what happens in our construction. You rotate this line from the eccentric point 90 degrees about its center, and the geometry enthusiasts in the room might fancifully call this a perpendicular bisector of the original line. Now take a moment to think about the sum of the distances from our proposed focus points to any point Q along this perpendicular bisector. The key insight here is that you can find two congruent triangles and use them to conclude that the distance from Q to the eccentric point is the same as the distance from Q to P. So that means that adding the distances to each focus is the same as adding the distance from the center to Q, then Q to P. And there are two key things that I want you to notice here. First, at the point where this perpendicular bisector intersects the radius, that sum is clearly just the radius of the circle. And since that radius is constant, no matter where we draw it, the focal sum at that intersection point stays constant, which by definition means that it traces out an ellipse. Specifically, an ellipse whose focal sum is equal to the radius of the circle. Isn't that neat? And second, because the sum of these two lengths at every other point on that perpendicular bisector is larger than the radius, meaning the sum of the distances to the foci from those points is bigger than the ellipse's focal sum, all other points of this line have to lie outside the ellipse. What that means, and this is going to be important, is that this perpendicular bisector, the line that we got after our special 90-degree rotation, is tangent to the ellipse. So, the reason that all of the lines that we drew earlier make this ellipse appear from nothingness is because we're basically drawing a whole bunch of the tangent lines to that ellipse. The reason that that's going to be important, as you'll see later, is that this tangency direction is going to correspond to the velocity of an orbiting object. Okay, geometry proofing is done. On to some actual physics and orbital mechanics. The first fact is to use Kepler's very beautiful second law, which says that as an object orbits around the sun, the area it sweeps out during a given amount of time, like one day, is going to be constant, no matter where you are in the orbit. For example, maybe you think about a comet whose orbit is really skewed. Close to the sun, it's getting whipped around really quickly, so it covers a larger arc length during a given time interval. But farther away, it's moving slower, so it covers a shorter arc length during that same time. And this trade-off between the radius and the arc length balances out in just such a way that the swept out area is the same. A quick way to see why this is true is to leverage conservation of angular momentum. For any tiny little time step, delta t, the area swept out is basically a triangle, right? In principle, you should think of this as a very small sliver for a tiny time step, but I'm going to draw it nice and thick so that we can better see all of its parts. The area of this triangle is 1/2 base times height, right? That base is the distance to the sun. And what about the height, this little length here? How do you find that? Well, it's going to be the component of the object's velocity perpendicular to the line of the sun, what I'll call v perp, multiplied by the small duration of time. So the full area is 1/2 times the radius times v perp times delta t. Now, conservation of angular momentum with respect to a given origin point, like this sun, tells us that this radius times the component of velocity perpendicular to it remains constant, so long as all the forces acting on the object are directed towards that origin. Well, specifically, it says that this quantity times the mass of the object stays constant, but the mass of the orbiting object isn't going to be changing. So, our expression for the area swept out depends only on the amount of time that has passed, delta t. Historically, by the way, this went the other way around. Kepler's second law is one of those empirical facts that led us to an understanding of angular momentum. And I should emphasize, this law does not assume that orbits are ellipses. Heck, it doesn't even assume the inverse square law. The only thing needed for this equal area property to hold is that the only force acting on an object is directed straight towards the sun. This is a fact that Feynman spent a lot more time showing, recounting an argument by Newton from his Principia, but it kind of distracts from our main target, so I figure assuming conservation of angular momentum is good enough for our purposes here, albeit at some loss of elementarity. At this point, despite my suggestive drawings, we don't know the shape of an orbit. For all we know, it's some wonky non-elliptical egg shape. The inverse square law is going to help us pin down that shape precisely, but the strategy is a little indirect. Before showing the shape of the path traced out by the orbiting object, what we're going to show is the shape traced out by the velocity vectors of that object. Here, let me show you what I mean by that. As the object orbits, its velocity will be changing, right? It's rotating, always tangent to the curve of the orbit, and it's longer at points where the object is moving quickly, and shorter at points where it's moving more slowly. What we'll show is that if you take all these velocity vectors and collect them together so that their tails sit at a single point, their tips actually trace out a perfect circle. Now this is an awesome fact, if you ask me. The velocity spins around, getting faster and slower at various angles, but evidently the laws of physics cook things up just right so that these trace out a perfect circle. And the astute among you might have a little internal light bulb starting to turn on at the sight of this circle with an off-center point. But again, we have to ask, why on earth should this be true? Feynman describes being unable to easily follow Newton at this point, so instead he comes up with his own elegant line of reasoning to explain where this circle comes from. He starts by looking at the orbit, whose shape we don't know, and slicing it into little pieces which all cover the same angle with respect to the sun. Alright, now think about the amount of time that it takes for the orbiting object to traverse one of these equal angle slices, and how that time changes as you go to a bigger slice. Well, by Kepler's second law, that time is proportional to the area of the slice, right? And because these slices have the same angle, as you get farther away from the sun, not only does the radius increase, but the component of arc length perpendicular to that radial line goes up in proportion to the radius. So, the area of one of these slices, and hence the time that it takes the object to traverse it, is proportional to the distance away from the sun squared. In principle, by the way, we're only going to be considering very small slices, so there won't be any ambiguity in what I mean by the radius, and the little arc length will basically be a little straight line. Alright, now think about how the inverse square law comes into play. At any given point, the force that the sun imparts on the object is proportional to 1 divided by the radius squared. But what does that really mean? What force is the mass of an object times its acceleration, the amount that its velocity changes per unit time. This is enough to give us a super useful bit of information about how the velocity of the orbiting object changes as it goes from the start of one slice to the start of the next. That change in velocity is the acceleration times the change in time, right? What that means is that this change to the velocity is proportional to the change in time divided by the radius squared. But since the time that it takes to traverse one slice is proportional to the radius squared, these terms cancel out. So the change in velocity as it traverses a given slice is actually some constant that doesn't depend on the slice at all. Here, unpacking what I mean by that, if you look at the velocity at the start of a slice, and then you look at the velocity at the end of that slice, and directly compare those two vectors by joining their tails, and you look at the difference between them, the little vector joining their tips. This difference has the same length no matter which slice of the orbit you were looking at. So, as you compare these velocity vectors at the start of each slice, they'll be forming some kind of polygon whose side lengths are all the same. Also, since the force vector is always pointing towards the sun, as you go from the start of one slice to the next, that force vector, and hence the acceleration vector, is turning by a constant angle. In geometry lingo, what this implies is that all the external angles of our polygon are going to be equal to each other. I know that this is a little tricky, but hang in there. Remember, all you need to follow along is infinite intelligence. It's worth reiterating just to make sure it's clear what's happening with this velocity diagram. The change from one vector to the next, this little difference vector joining the tip of one to the tip of the next, always has the same length. That was the consequence of the perfect cancellation between mixing Kepler's second law with the inverse square law. And because those constant length change vectors rotate by a constant angle each time, it means that they form a regular polygon. And as we consider finer and finer slices of the original orbit, based on smaller and smaller angles for those slices, the relevant regular polygon defining the tips of these vectors in the velocity diagram approaches a perfect circle. Isn't that neat? Hopefully, at this point, you're looking at the circle. You're looking at the eccentric point, and you're just itching to see how this gives rise to an ellipse the way that we saw earlier. But it's a little weird, right? I mean, we're looking at this diagram in velocity space, so how do we use that to make conclusions about the actual orbit? What follows is tricky but clever. Step back and consider what we know. We don't know the specific shape of the orbit, only the shape that the velocity vectors trace. But more specifically than that, we know that once the planet has turned an angle theta degrees off the horizontal with respect to the sun, that corresponds to walking theta degrees around our circle in the velocity diagram, since the acceleration vectors rotate just as much as the radius vectors. This tells us the tangency direction for each point of the orbit. Whichever vector from that velocity diagram touches the point theta degrees around the circle, that's the velocity vector of our orbiting object, and hence the tangency direction of the curve. In fact, let me just start drawing all these vectors as lines, since all we're going to need to use is the information they carry about the slope of the orbit curve. The specific magnitude of each velocity will not be as important. Notice, what I'm not saying is that the angle of the velocity vector at this point is theta degrees off the vertical. No. The angle I'm referencing in the velocity diagram is with respect to the circle's center, which is almost certainly a little different from where the velocity vectors are all rooted. So the question is, what special curve satisfies the property that the tangency direction, the slope, for a point theta radians off the horizontal is given by this vector from a special eccentric point of the circle to a point theta degrees around that circle from the vertical? Okay, is the question clear? Well, here's the trick. First, rotate the whole circle setup 90 degrees, and then take each of those individual velocity directions and rotate them 90 degrees back the other way. That way they're oriented just like they were before, it's just that they're rooted in a different spot. Aha! We've spotted our ellipse, but we still have a little bit of thinking ahead of us to really understand how this little emergent ellipse is related to the astronomical orbit. Importantly, I didn't just rotate these lines about any point. I rotated each one of them about its center, which means we can leverage the geometric proof we saw a few minutes ago. And this is probably the moment where you kind of have to furrow your brow and think back, okay, wait a minute, what was going on in that proof again? Well, one of the key points was that when you have two lines, one from the center of the circle and one from the eccentric point, both to a common point on the circle's circumference, the perpendicular bisector to the eccentric line is tangent to the ellipse. And what's more, the point of tangency is where that perpendicular bisector intersects the radial line from the center. What that means is that the point of our little ellipse, which is theta degrees off the horizontal with respect to the circle's center, has a tangent slope perpendicular to the eccentric line. And because of the whole 90-degree rotation thing, this means that it's parallel to the velocity vector that we need it to be. So, this little emergent curve inside the velocity diagram has exactly the tangency property that we need the orbit to have. And hence, the shape of the orbit must be an ellipse, QED. Okay, pat yourself on the back, because there is no small amount of cleverness required to follow this. First, there was this peculiar way of constructing an ellipse, which requires some geometry savviness to properly prove. And then there's the pretty clever step of even thinking to ask the question about what shape the velocity vectors trace out when you move their tails to the same spot. And showing that this is a circle requires mixing together the inverse square law with Kepler's second law in another sly move. But the cleverness doesn't end there. Showing how this velocity diagram, with vectors rooted at an off-center point, implies an elliptical orbit, brings in this very neat 90-degree rotation trick. I just love this. Watching Feynman do physics, even elementary physics, is like watching Bobby Fischer play chess.
Thanks again to Grant, and you should definitely go check out his videos on 3 Blue 1 Brown.